is the example I used before for how to calculate average standard deviation in t-test. I'll do it one more time over video so that you can have your own results up and do each of these steps one by one. Feel free to speed this video up or slow it down. I encourage you to pause and do each of the steps on your own spreadsheet after you watch me do them. Alright, so my research question as my example was, does 1 month of 30 minutes per day, 4 days per week of bicycle commuting improve insulin sensitivity in people at risk of developing type 2 diabetes? Hypothesis, prediction, multiple measures of insulin sensitivity will improve after a month of bicycle commuting. The dependent variable that I'm going to show here, among multiple that I would have measured in this example study, is fasting blood glucose. What is blood sugar, blood glucose, right after waking without having a meal? So we've got our control group. They were driving, and I recruited 4 people, and this is their fasting blood glucose after that month. And I recruited 4 other people, and I put them in the bicycle group. They did their bicycle commuting according to the 30 minutes per day, 4 days per week, and this is their fasting blood glucose. At first look, blue does look a little lower. I see some 90s where I don't see any 90s in control, but I do see blue had someone at 110, and that was almost as high as the highest one I see over in the driving group. And this 105 is higher than this 104 in the driving group, and it's the same as this 105. So quick look, yeah, this looks a little lower, but I certainly see some people that are just as high or higher than some of the people in the driving group. So this is why we don't just use raw results. We're going to calculate some statistics so that we can rely on other people's predetermined, okay, this is safe enough type of ideas of determining whether there was an effect of a treatment, rather than just eyeballing it. We want to be more secure in science than eyeballing it. So average, you're going to press the equals button and you're going to type average. As soon as this pops up, feel free to just click it. Average, it's going to open a parenthesis, and then you'll select your raw data. In this case, my 4 people in the driving group. And press enter. Standard deviation, you're going to type equals STDEV. Again, as soon as you see it, you can press it, or you can select the tab button. Either one will select it. Opens parenthesis, and again, select just the raw data. My 4 individuals in the driving group. Do not select average. Make sure you keep it on just those 4. And enter. Highlight both of those, and you can go to the bottom right-hand corner and click on that little box and drag it over to the 2 that are underneath the bicycle group. You can do it again by hand, equals average and select your numbers, equals standard deviation and select your numbers, but this is a nifty trick that does it automatically. It's saying copy the formula over, but keep the reference relative. So it was referring to the 4 cells between rows 5 and 8. So when you drag that over, it changed it from B5, B8 to C5, C8, because it's over 1, so the reference came over 1. Again, I am seeing the same trends I was seeing eyeballing it. A slightly lower bicycle group fasting blood glucose than my driving group. And my standard deviation is a measure of how spread out the group is. This is pretty close for values like this. Standard deviation of 20 or 30 for blood glucose would be a lot of variability. But they're both about the same. So even if you don't know what the normal spread of data is for your variable, as long as they're both the same, then I'd say they have equal variability or similar variability. How spread out variability, meaning how spread out are they? Again, I still need a better statistic than this. This is still kind of eyeballing statistics land. So let's go t-test, which is equals t dot test click it, and then you're going to select your first 4 pieces of raw data, enter a comma, your next 4, comma, and all of us, regardless of what kind of data you're using, will use a 2-tailed distribution. So type 2 and comma, and all of us will be using a 2-sample equal variance, meaning the individuals in the first group are not the same individuals as are in the second group. That would happen when you do a before and after type scenario. So same person, but it's the number beforehand and after. That kind of thing. But all of us are doing a 2-sample equal variance. So type the number 2 and press enter. And this will give you your t-test. Your t-test has to be, well, it doesn't have to be. Science tells you what it tells you. Nothing has to be anything. What this is showing is that it is more than p-value. That's what this number is. It's a p-value from a t-test. Your p-value is greater than or equal to 0.05. There's no significant difference between the groups for this dependent variable. So I would present this as no difference in blood glucose values between control and bicycle commuting group. Averages were 109 versus 103 with a standard deviation of 5 versus 6. But despite that numerical, I hesitate to say the word difference, despite the fact that this numerically is higher than this, statistically it's not higher. This is just random chance that this one is a little higher. And I hope you can make sense of that, because look at, there are 2 individuals in this group that are high or higher than the individuals in this group. So we don't want to just trust the average. This shows maybe there's something more here. And it doesn't, I'm not convinced that these groups are truly different. So you need to make a slide. So copy that, go into your PowerPoint, name one of your slides, whatever your dependent variable is. Dependent variable, fasting blood glucose. And copy in your little graph. I liked it as it was. Odd that I lost my formatting there. I'm going to try that again. Paste special. I'm going to paste. Oh, I can actually just paste it as a picture. Or I might be able to paste it as formatted text. Nope. Paste. Let's insert it as a picture. Now I got to keep those nice, all the nice colors. You can feel free to do it either way. Recolor it as you please. Doesn't matter to me. And just add no significant difference between groups. All right. So far, I have not said anything about my hypothesis. I am just presenting data on these conditions. I do want a graph as well, though, so I'm going to highlight my raw data. I'm going to go to Insert. I'm going to do a bar graph, column graph for this. No, I don't want raw results. That looks like a mess. So absolutely not. Raw data does not look good. Let's do averages. So for this, Just quickly make a mini table. Paste my values. Paste my titles. Let's just graph our average results. Insert bar. There we go. I like that. All right, they're already labeled nicely on the x-axis, but I need a label on my y-axis because otherwise I don't know what the heck these numbers are. Add chart element, axis title, vertical. This is fasting. Blood glucose. Units are mgs per mil, I think. That doesn't seem right. What are my units? Units of fasting blood glucose. I should know this, but hey, I don't, so use the internet. Mgs per deciliter, not mgs per mil, mgs per DL, deciliter. Mgs per deciliter. All right. You may format it to different colors if you like, or just stick with what it gives you. All right. Feel free to make this look prettier than I've made it. But this is pretty... it's pretty solid. I've got a data table showing my results. I have a graph that also shows my results. And during a presentation, I can talk more about both of these. Now, the one other complication is you haven't talked about your hypothesis yet. So whoever's in charge of the slide for your discussion section of your slides, you need to communicate to them what's going on. So hypothesis was multiple measures of insulin sensitivity will improve after a month of bicycle commuting. Let's say I measured 3 different dependent variables for this. The one I just went through was fasting blood glucose. Fasting blood glucose decreased. No, it did not. Whoa, I just fell for it. It looks like it decreased, but it didn't. There is no significant difference. Especially if there is no significant difference, it's helpful for you to give the graphs zoom in. Really, fasting blood glucoses can go way down. So when you make it a little more physiologically relevant, these can get up to, let's say, 200. They can get as low as 50-ish. It can get lower, can get higher, but especially when you put it in a more physiologic realm of these numbers, you can see there really is no difference. It only looks like a difference when you're zoomed in super far. Fasting glucose, no change, right? Because there was no significant difference between the groups. So, no change. All right. I should justify this, though. P value equals 0.195. 0.195. All right. Now, someone else would calculate your hemoglobin, your oral glucose tolerance test, and maybe hemoglobin A1C does change. give a p-value, but that p-value has got to be less than 0.05 for you to say something changed. And maybe my oral glucose tolerance test also changed. So I end up with a no change on fasting blood glucose, but hemoglobin A1C changed, oral glucose tolerance test changed. That doesn't mean your hypothesis or prediction or your whole idea is wrong. It could mean that your independent variable doesn't affect fasting blood glucose levels, but it does affect oral glucose tolerance test. That's fine. It doesn't have to affect all measures of, in this case, glucose tolerance, insulin sensitivity. All right, so you are going to do this same thing, but with your data. I have provided on D2L a link to an empty spreadsheet like this that has plenty of room for all your control plants raw data and all of your experimental plants raw data from that last week of data collection for that variable. Just focus on that last week. We call this endpoints. It is the last time you were measuring that thing from beginning to end rather than a continuous. And replicate what I did. And that should get you everything you need. All right. Good luck.